Have you ever wondered why software written for an Nvidia GPU cannot simply run on an AMD GPU? Even though both companies manufacture powerful GPUs, their hardware architectures and programming ecosystems are very different. This means that developers who have invested years building CUDA applications often have to spend significant time and effort rewriting their code if they want to run it on AMD hardware. But what if we could automatically translate GPU programs from one vendor to another? That is exactly the problem addressed in today's research paper. CASS, Nvidia to AMD Transpilation with data, models, and benchmark. In this video, we'll explore how the authors created the first large-scale dataset specifically designed for GPU code transpilation. We'll also see how they trained specialized language models that can translate not only GPU source code, but also low-level GPU assembly instructions from NVIDIA's architecture to AMD's architecture. What's particularly interesting is that these models don't just generate code that looks correct. They produce translations that compile, execute correctly, and in most cases preserve the original runtime and memory behavior. We'll also learn about CASS Bench, the first benchmark created specifically to evaluate cross-architecture GPU transpilation, and compare the proposed models against popular systems like GPT 5.1, Claude 4.5, and AMD's own Hippify tool. By the end of this video, you'll understand why GPU transpilation is a difficult problem, how the CASS dataset was built, how the proposed models work, and why this research could make GPU software much more portable across different hardware vendors. So, without wasting any more time, let's get started. Now let's look at how the authors actually built this dataset. The first step was gathering real-world CUDA programs. The authors used the Stack v2 dataset, which is a large collection of deduplicated and license-compliant source code from public repositories. Instead of downloading individual CUDA files, they selected the top 200 repositories, containing the largest number of CUDA programs. This might sound like a small implementation detail, but it made a big difference. By downloading entire repositories instead of isolated files, they preserved the original folder structure, header files, and dependencies between source files. As a result, the number of programs that successfully compiled increased by almost 24% compared to scraping individual files. After downloading the repositories, the authors cleaned the dataset by removing files that were too large, too small, and programs that didn't actually contain CUDA kernels. After this filtering process, they obtained around 24,000 high-quality real-world CUDA programs. Although 24,000 programs is a good start, it still wasn't enough. GPU programming is a specialized field, and many types of kernels are rarely available in public repositories. If the dataset only contained existing code, the translation model would struggle with less common GPU workloads. To solve this problem, the authors generated additional CUDA programs using a large language model called Qwen 2.5 Coder 32B. Instead of asking the model to generate random code, they created prompt templates with placeholders. For example, a prompt could be, the placeholders were automatically replaced with different values. For instance, the grid size could be 32, 64, or 128, while the optimization objective could focus on memory bandwidth, register usage, or multi-GPU scaling. By combining these variables, the authors could automatically create thousands of unique prompts, each producing a different CUDA program. Of course, LLM-generated code isn't always correct. Some programs contained syntax errors, undefined variables, or invalid memory accesses. Therefore, every generated program went through an extensive filtering process, where only successfully compiling programs were kept. In total, the authors generated around 85,000 synthetic CUDA programs. About 49% of them compiled successfully, resulting in approximately 20,600 valid synthetic CUDA files. When combined with the real-world code collected earlier, this provided a large and diverse collection of CUDA programs that formed the foundation of the CASS dataset. Now that the authors had both real-world and synthetic CUDA programs, the next step was to convert them into code that could run on AMD GPUs. Before doing any translation, they first performed a deduplication check to make sure there were no duplicate programs in the dataset. The first stage of translation was performed at the source code level using AMD's Hipify tool. Hipify automatically replaces CUDA-specific API calls with their HIP equivalents, allowing the same program to be compiled using AMD's ROCm software stack. However, this process wasn't perfect. Nearly 44% of the CUDA files failed to convert successfully and had to be discarded. Only the successfully translated CUDA HIP pairs were kept for the next stage. Once the source code pairs were ready, the authors compiled both the Nvidia and AMD versions into their corresponding assembly languages. To reduce the size of the generated assembly code, they used the OS compiler optimization flag, which focuses on minimizing code size instead of maximizing performance. This simple decision reduced the average number of assembly tokens by about 9.3% compared to using the more aggressive O3 optimization level. One of the biggest challenges was that Nvidia and AMD have completely different compilation pipelines. On the AMD side, the ROCm compiler normally embeds the GPU device binary directly into the host executable during compilation. That behavior made it difficult to obtain separate CPU and GPU assembly code. To solve this, the authors modified the compilation pipeline so that the embedding step happened later. This allowed them to extract the host assembly and device assembly independently and recombine them only when needed. Nvidia's toolchain presented a different challenge. Unlike AMD, Nvidia does not provide an official way to separate or reinsert the GPU binary during compilation. The host and device assembly remain intertwined, making analysis much more difficult. Since the goal of this work was to translate host code separately from GPU device code, the researchers developed a custom, regular expression-based filtering pipeline that could identify and separate the host and device assembly sections from Nvidia's compiled output. Finally, the authors kept only those programs that compiled successfully on both the Nvidia and AMD toolchains. The resulting dataset contains matched CUDA HIP source code, Nvidia CASS assembly, AMD RDNA3 assembly, and the corresponding host CPU assembly. After completing this entire pipeline, the authors assembled a dataset containing approximately 64,000 verified samples, providing the first large-scale resource for both source-level and assembly-level GPU transpilation. To make the dataset even more diverse, the researchers introduced an additional pipeline based on OpenCL. Unlike CUDA and HIP, OpenCL is an open standard for GPU programming. Instead of being tied to a specific vendor, the same OpenCL source code can target GPUs from different manufacturers. This makes it an excellent source for generating additional Nvidia to AMD assembly mappings. The authors collected approximately 6,000 OpenCL programs from the stack dataset and compiled them for both Nvidia and AMD hardware. On the Nvidia side, they first wrapped the OpenCL code inside a C++ function that called the CL build program library. This allowed the code to be compiled into PTX, Nvidia's intermediate representation, which was then further compiled into SAOS assembly using the CUDA toolchain. On the AMD side, the process was more straightforward. They used the CLang compiler to directly compile the OpenCL programs into RDNA3 assembly, while also forcing the compiler to generate intermediate LLVM code during compilation. The completed dataset contains 60,694 verified and aligned samples covering a wide variety of GPU applications and data structures. Each sample includes the original CUDA source code, its corresponding HIP source code, the compiled Nvidia SAS assembly, and the equivalent AMD RDNA3 assembly. All compilations were performed on an Nvidia A100P CIE machine for the CUDA stack and on AMD Radeon RX 7900XT for the AMD stack. Now let's look at the CASS dataset. One of the first things the authors analyzed was how different Nvidia and AMD code actually is. The researchers first compared the lengths of the generated assembly files. Interestingly, they found that AMD's device assembly is on average about twice as long as Nvidia's for synthetic datasets. However, when using the OpenCL pipeline, the trend was reversed, with Nvidia's device assembly becoming roughly 50% longer than AMD's. Another important observation was that as the source code becomes more complex, the assembly code grows exponentially in size rather than linearly. The authors also analyzed the different instructions, or opcodes, used by both GPU architectures. They found that both Nvidia and AMD rely heavily on instructions related to tensor computations, memory operations, and control flow, which makes sense because these are fundamental building blocks of GPU programming. However, each architecture also has its own unique instruction set. For AMD, instructions such as S_move_B32 and V_add_CO_U32 appeared very frequently. These are low-level vector and memory operations that expose many details of AMD's hardware. On the Nvidia side, instructions like moveqcall and jump were much more common, reflecting a stronger interaction between the CPU host code and GPU device code. Even though the instruction names differ, the authors wanted to know whether they actually represent similar operations. To answer this, they generated embeddings for the opcodes using code BERT and visualized them using TSNE. The visualization showed that many Nvidia and AMD instructions form similar semantic clusters, suggesting that although the two architectures use different instruction sets, many instructions perform equivalent operations. This is encouraging because it indicates that a translation model can potentially learn meaningful mappings between the two architectures. To fairly compare different transpilation systems, the researchers also created CASS Bench, the first benchmark specifically designed for cross-architecture GPU translation. CASS Bench contains 369 carefully selected samples covering both CUDA to HIP source translation and CASS to RDNA3 assembly translation. The authors performed strict deduplication so that the benchmark measures how well a model generalizes to completely unseen programs, instead of simply memorizing examples from training. To ensure correctness, the outputs produced on both platforms were compared using automated differential testing. Finally, the benchmark spans 18 different GPU application domains, providing a diverse and challenging evaluation set for measuring the performance of future GPU transpilation systems. With the CASS dataset and CASS Bench ready, the next step was to train models capable of performing GPU code translation. Instead of building a model from scratch, the authors started with Qwen 2.5 Coder. Interestingly, they trained two separate models. The first model was designed for source-level translation, converting CUDA code into HIP code. The second model focused on the much harder task of assembly-level translation, converting Nvidia's SAS assembly into AMD's RDNA3 assembly. Before training could begin, the authors had to make sure the input programs fit within the model's context window. To solve this, they cleaned the CUDA assembly by removing unnecessary whitespace and comments. This simple pre-processing step reduced the number of tokens by approximately 15%, allowing more programs to fit within the model's maximum input length. One interesting detail is that they did not perform the same pre-processing for AMD's HIP assembly. The reason is that changes in whitespace could affect how the HIP assembly was interpreted, so the authors chose to leave it untouched. The researchers fine-tuned 3 different versions of Qwen 2.5 Coder, containing 1.5 billion, 3 billion, and 7 billion parameters. Training was performed on 4 Nvidia A100G GPUs. To improve training efficiency, they used several optimization techniques. They trained with an effective batch size of 512 and selected a relatively high learning rate of exponent -5. The authors explain that this aggressive learning rate was necessary because GPU assembly code is very different from the programming languages that these models originally saw during pre-training. They use deep speed, which distributes optimizer states across multiple GPUs, allowing larger models to be trained efficiently. They also incorporated the Liger kernel, which speeds up transformer computations, and the paged Atom optimizer, which manages GPU memory more effectively during training. To simplify the implementation of all these optimizations, they relied on Llama Factory, an open-source framework for fine-tuning large language models. Thanks to these optimizations, the training process achieved an impressive 98% GPU utilization. All of the models were trained with a 16,000 token context window, allowing them to process fairly large GPU programs. However, many real-world assembly files are even longer than that. To address this limitation, the authors applied rope extrapolation during inference, extending the maximum context length to approximately 32,700 tokens. Now comes the most exciting part of the paper: how well do the case models actually perform? The authors evaluated their models on CASS bench and compared them against several well-known commercial and open-source systems. Let's first look at the assembly-to-assembly translation results. This turned out to be an extremely challenging task. Even today's most advanced language models struggle to translate Nvidia's CASS assembly into AMD's RDNA3 assembly. For example, GPT 5.1 achieved an accuracy of only 22.22%. Surprisingly, even the coding-focused Qwen 2.5 coder 32B performed much worse, reaching only about 5.42% accuracy. Another baseline, ZluDA, achieved just 7.86%. So why is this task so difficult? The authors explain that the biggest reason is the lack of training data. Unlike programming languages such as Python or C++, CASS is a proprietary and largely undocumented instruction set. Since very little CASS code exists publicly, general-purpose language models simply don't see enough examples during pre-training to learn how it works. ZluDA faces a different limitation. Rather than translating native GPU assembly, it operates at the LLVM intermediate representation level. While this allows it to support multiple architectures, it misses many hardware-specific optimizations that exist only in Nvidia's CASS assembly, such as instruction scheduling and register allocation. On top of that, Nvidia and AMD use fundamentally different instruction set architectures. For example, CASS uses fixed 16-byte instructions with built-in timing information for latency hiding, whereas RDNA3 uses explicit synchronization instructions and separates scalar and vector execution pipelines. Because of these architectural differences, assembly translation is much more than simply replacing one instruction with another. Now, how well did CASS perform? This is where the proposed approach stands out. The CASS SM87B model achieved an impressive 69.11% assembly translation accuracy. Compared to GPT 5.1's 22.22%, this represents a massive improvement. This result clearly demonstrates the value of domain-specific fine-tuning for highly specialized programming tasks. The authors also investigated where the model still makes mistakes. They found that most failures occur because the generated assembly contains invalid instructions or incorrect operand combinations. These errors become especially common in computation-heavy applications, such as vector operations and linear algebra, where the instruction sequences are significantly more complex. The authors also compared the runtime and memory usage of the translated programs against code generated directly by the native compiler. The results were very encouraging. The runtime distributions of the translated programs almost completely overlapped with those of the ground truth implementations. GPU memory usage differed by less than ±0.3 megabytes, while execution time differed by no more than ±1.5 seconds. Even more impressively, over 95% of all translated programs finished within just ±0.5 seconds of the native implementation. To ensure these measurements were reliable, every benchmark was executed 20 times, and the reported results represent the average across all runs. Now let's move to source-level translation, where the goal is to convert CUDA source code into HIP's source code. Not surprisingly, this task is much easier. The best CASS model achieved an impressive 88.17% accuracy, significantly higher than the 69.11% obtained for assembly translation. So why is source translation easier? The answer lies in the way HIP was designed. Unlike AMD's assembly language, HIP was intentionally created to closely resemble CUDA. In many cases, converting CUDA to HIP simply involves replacing the CUDA prefix with HIP. Beyond these API name changes, both programming models share the same C++ foundation, including templates, classes, lambda expressions, and function signatures. Because of this high similarity, the authors measured a CHRF score of around 90%, indicating that CUDA and HIP source code are syntactically very close. This is also why AMD's Hipify tool can successfully translate many CUDA programs using relatively simple rule-based string replacements. However, not every CUDA program can be translated with simple text substitutions. Some CUDA features require an understanding of the program's meaning rather than just its syntax. For example, CUDA supports inline PTX assembly, which has no direct equivalent in HIP. Similarly, some programs assume that a GPU warp always contains 32 threads, while AMD hardware uses 64-thread wavefronts. A translator must recognize these architectural differences and modify the code accordingly. There are also CUDA-specific intrinsic functions and architecture-dependent preprocessor directives that cannot be handled correctly using simple pattern matching. These cases require semantic reasoning about what the code is actually trying to accomplish. Now, let's compare the performance of CASS with HIPify. This is where the proposed model demonstrates another interesting result. Although the CASS source translation model was trained using data generated by HIPify, it actually performed slightly better than HIPify itself. The CASS model achieved 88.17% accuracy, compared to 87.46% for HIPify. At first glance, this might seem surprising. How can a model trained on HIPify's outputs outperform the very tool that generated its training data? The authors describe this as a form of self-improvement. Instead of simply memorizing the text replacements performed by HIPify, the language model learns the underlying semantic relationship between CUDA and HIP. As a result, it can correctly translate certain edge cases where HIPify's rule-based approach fails. Next, the authors performed an ablation study, where they removed one component at a time and observed how the model's performance changed. The most significant improvement came from the synthetic data generated using a large language model. Adding these AI-generated samples increased the translation accuracy by 11.65%. This highlights an important finding. Real-world GPU code available online is relatively limited and often lacks diversity. By generating synthetic CUDA programs, the authors introduced many GPU workloads that rarely appear in public repositories. Another interesting contribution came from the OpenCL pipeline. Even though it added only around 6,000 samples, it still improved the model's accuracy by 5.34%. The reason is that OpenCL follows a different compilation pipeline than CUDA and HIP, exposing the model to new instruction patterns and memory management techniques. The authors also evaluated the impact of rope extrapolation, which extends the model's context window during inference. This technique provided an additional 3.88% improvement, allowing the model to better handle long assembly files. Next, the authors investigated an important question. Can a model trained on one Nvidia GPU architecture successfully translate assembly generated for another Nvidia GPU architecture? To test this, they trained their model using assembly generated on an Nvidia A100 GPU, which uses the SM80 architecture, and then evaluated it on assembly produced by an RTX 4090, which uses the newer SM89 Ada Lovelace architecture. The results were surprising. The translation accuracy dropped dramatically from 69.11% to just 32.5%. This happened even though both GPUs were manufactured by Nvidia. Why such a large drop? The answer is that GPU instruction sets continue to evolve across hardware generations. For example, the newer architecture introduces FP8 tensor instructions that do not exist in the older generation. It also changes instruction scheduling, register allocation strategies, and memory access patterns because of architectural improvements such as a much larger L2 cache. This experiment highlights an important takeaway. GPU assembly translation is not just a problem of translating between Nvidia and AMD. It is also a problem of translating across different GPU generations, where even hardware from the same vendor can produce significantly different assembly code. Finally, the authors analyzed how the length of the input program affects translation quality. As the assembly code becomes longer, both the translation accuracy and the compilation success rate decrease significantly. In fact, for programs longer than 750 lines, the translation accuracy approaches zero. There are two main reasons for this. First, longer programs naturally contain more complex control flow, memory accesses, and interactions between instructions, making the translation task much more difficult. Second, today's large language models still struggle with very long contexts. Even with techniques such as rope extrapolation, the quality of the attention mechanism gradually decreases as the input sequence becomes longer. Now, let's wrap up with some limitations of the research project. One of the biggest challenges is support for tensor core and other matrix-oriented GPU operations. Many modern AI workloads rely heavily on these specialized instructions for accelerating deep learning computations. Unfortunately, AMD's current Hippify tool does not fully support translating several CUDA-specific features, including WMMA, tensor core operations, and some low-level CUDA primitives. Because of these missing mappings, programs that depend heavily on tensor core instructions often fail to translate or compile successfully. The authors also experimented with additional AMD libraries such as HIP-BLAS and HIP-Tensor, hoping to improve coverage. However, these additions provided only limited improvements because of restrictions in the current compilation pipeline. The good news is that this limitation is likely temporary. As the ROCm ecosystem and Hippify continue to evolve and support more CUDA features, the CASS dataset can also grow to include richer tensor and matrix workloads. This would allow future translation models to handle an even wider range of GPU applications while preserving both correctness and performance. That brings us to the end of this paper. If you'd like to dive deeper into the technical details, I highly recommend reading the original research paper. I've included the link in the description below. If you found this video helpful, don't forget to like the video and subscribe to the channel. Thank you for watching, and I'll see you in the next video.